and we try to estimate what is the energy content of a fuel, what kind of temperatures will you get when you burn that fuel, right? With an appropriate amount of oxidizer, if you supply it along with an ignition energy, then what will be the approximate theoretical value of the temperatures, flame temperatures that you will experience. Okay, so what are those temperatures called? Anyone remembers? Adiabatic flame temperatures, and we derived an expression for constant pressure systems, and we saw that those are constant pressure, constant enthalpy processes. All right. So today what we are going to do is, now that we have understood how we can calculate energy content and what could be the flame temperatures that are important to us, the next part is how fast a reaction happens, right? Yesterday in the afternoon session with Professor Sunil Kumar's session, you were doing some FDA simulations. So one of those parameters, if you remember, it was some heat release rate per unit area, right? So what is that heat release rate? How do you get that? So that is basically happening because of how fast your reactions happen. So in that, to understand that, we have combustion kinetics to help us out, right? So yesterday we looked at this flame propagation, correct? And how fast this flame is propagating is something that we are interested in, right? So to determine how fast a combustion process happens and how it affects the flame propagation rate, other phenomena like flashback and blowout, which are important for you to have stable combustion, and as well as to calculate these heat release rates, you need to understand combustion kinetics. Okay. So now, if you look at, if I freeze this flame front at a particular location, and if I zoom in, what is this basically representing is, this is your flame front, okay, your reaction zone that is taking place, exothermic reaction zone. On the downstream side, you have your burnt mixture, so these are all burnt products, and on the upstream side, you have unburnt fuel air mixture, correct? So, and progressively, the flame front is trying to consume the fresh air mixture, fresh fuel air mixture, and it is progressing ahead. Alright, so now I ran a simple 1D flame simulation, and if I plot the various properties, what we will see here is, so you can see on the x-axis you have distance, right? So this is 0 to 5 centimeters, so there is a 5 centimeter length that I have taken, a domain that I have taken, and I have simulated this flame front. So what you see is, on the left hand side, y-axis, these are mole fractions. On the right hand side, these are the temperature, okay? So this red line is basically representing the temperature as you go from the upstream side to the downstream side. So initially you have, you have 300 Kelvin, which is your ambient temperature, and you see suddenly the temperature has risen up to around 2200 Kelvin, right? So 2200 Kelvin is what we got yesterday, right? For methane air mixture, adiabatic flame temperatures were of that order. So you see that the temperature is rising sharply. And also, if you look at the mole fractions, now species compositions, for example, methane is this green line, and oxygen is this dashed line, short dashed line. You see that they are constant till a certain time, and after that it suddenly drops, right? That means they are basically getting consumed in this narrow region, and as they are getting consumed, your products of combustion that are CO2 and H2O are basically rising up, correct? So now if you want to appreciate this, you look at the thickness, the size of this domain, right? So it is very, very narrow. So you have a 5 centimeter domain, and within that also these are basically taking place as if it's instantaneously happening. Now if you zoom it in, so these are basically zoomed in views of that. So now what we have done is, I have zoomed into that flame region, and you can see that this is the temperature profile. So you can see a much more generous gradient. So you can look at the temperature rising, and this temperature rising is happening within, so this is around, let's say, 2.05 centimeter, and now it has almost reached around 2000 Kelvin by 2.15 centimeter, right? So that is roughly around 1 mm. Okay, so all the temperature rise is happening within 1 millimeter space. Okay, so you can see how thin these flame fronts are. And similarly, you can see all these reactions, consumptions are also happening within that same length, correct? Now these are, so on the right hand side, so what I have done is, along with the species concentration profiles, I have plotted a heat release rate profile. So this red solid line is basically representing the heat release rate that is happening. Okay, so heat release rate will happen because of what? Heat release will happen because of exothermic reactions, right? Overall, exothermic, endothermic, both type of reactions are there, but the net effect is the exothermic reaction. Because of that, you have the heat release happening. So if the heat release is happening in this domain, everyone said it is almost 0. So what that means is all your combustion reactions are happening within this narrow zone of 0.5 mm. Okay, so that means even if you have, like you look at this large space and if you further zoom in, you will get that all your reactions that are happening within this 0.5 mm of space within a combustion front. Okay. Now, in order to estimate this, so this is one of the values that you probably need during your FDS simulations, right? And to calculate this, right, in order to calculate the heat release rate, you need to understand how fast these reactions are going on and how it depends on the fuel composition. So if you look at this generic species conservation and energy conservation equations, so you will see that you have, like for species conservation equations, you have this term that is basically showing the rate of change of mass of a particular species per unit volume, right? So, and on the energy equation, energy conservation equation term, you again have a source term which is basically representing the rate of enthalpy increase that is associated with a particular species. So the summation of all those things will basically give you the heat release because of the chemical kinetics. Okay. So what we want to understand is, in order to solve these conservation equations, we need to understand how fast a particular fuel, oxidizer or any species is getting consumed or produced, right?
Excuse me, sir.
Yes.
What is the subscript A?
A is basically a species. So if you remember yesterday, so if you have a generic reaction, right? C plus D. So you want to see how fast this species is going. So A basically represents one species. So similarly, you will have B, C, D, whatever the number of species, right? Okay. So now let's look at this. So yesterday we looked at a generic your stoichiometric methane air combustion reaction, right? So this is one way how you can determine, like represent this methane oxidation or methane combustion reaction. Okay, so in case 1, your fuel has to interact with oxygen molecules so that it gets converted to CO2, carbon dioxide and water vapor, correct? So this is one way to represent. The other way to represent is going through this like a series of reactions, right? So if I ask you in reality, in practical situations, what happens? Does your methane directly react with oxygen, or does it go through this series of steps? Series of steps. Why do you think so? Why is this not happening? Why is there not a direct conversion of methane by oxygen to CO2 and H2O?
There is no pure oxygen.
Okay, so they both are molecular reactions.
No, like for each element, like they have different processes of molecular reaction.
Right, but what is the problem of this?
It is a stable structure. CH4 is a stable structure.
CH4 is a stable structure. Oxygen is also a stable structure. But once you start, so if you look at here also CH4 is a stable structure, right? But that when you supply that initial energy, it will distance, yes, it will break.
It's not such sufficient energy to direct do the reactions.
Okay, okay. So, all right. So when we are looking at these reactions that are taking place, you have to kind of look at the probability of this reaction happening versus the other reaction happening, right? So, for example, if you want to look at the left-hand side reaction, okay, so if I draw a CH4, so this is a CH4 molecule, right, and then you have, so these two molecules have to interact with each other, okay. Now from this to go to directly CO2, you basically have to break all these bonds simultaneously. Okay, and then this goes and attaches to form CO2. Okay, so the bond between these guys have to break, and then they have to reconfigure and adjust so that they form the CO2 molecule. Right? Now the probability of this happening is way less, right? Is way less than a single bond breaking, provided you have sufficient energy, right? So this is more likely to happen than simultaneous breakage of 1, 2, 3, 4, 5 bonds, and then this is rearranging to produce 2 more bonds. So it does not happen in a single step. So it has to go through this simpler steps where this one breaks to form a methyl radical, right? And then you will have so methane can directly react with oxygen as well, but it will produce a CH3 plus HO2 rather than CO2 and water vapor, right? So it goes through these series of simple steps, and we call these reactions as elementary reactions, right? Series of simple steps to basically finally give you the net product is going to be carbon dioxide and water vapor and other intermediate species, but it goes through this series of simple steps, and these are called as elementary reactions. In elementary reactions, what you will see is it basically involves breaking or forming of maximum of 1 or 2 bonds. Okay, so in this case you are breaking 1 bond, right? In this case you are breaking 1 bond, forming 1 bond. So these kind of the number of breaking and forming of bonds is basically limited to 1 or 2 in these kind of elementary reactions. Okay, but the net effect of all these reactions taking place in a combustion scenario is going to give you this, what is called as your global reaction. So this is a global reaction, and these all are your elementary reactions. Okay, so whenever you are now trying to understand these heat release and how the mole fractions are, how the fuel and oxidizer are getting consumed, in many cases we want to go through this, build this kind of detailed chemical kinetic models so you can simulate the various aspects more accurately. All right. So now that we have understood that these kind of elementary reactions are what are important to basically model a combustion process, we now want to understand how we can get the rate of reaction. That is ultimately what we want to do. So if you have a reaction that is A moles of A with B moles of B is giving C moles of C and D moles of D, then how can we get write an expression for how fast the A is getting consumed or produced, right? So we have a law of mass action, which basically says that the reaction rate of a chemical species, chemical process is proportional to the product of concentration of reacting species raised to the power of stoichiometric coefficients. So when you have an elementary reaction, then basically what you can say is the reaction rate of this forward process, that is RRF, is basically proportional to your concentration of the reacting species, that is A and B, right, raised to the power of the stoichiometric coefficients, that is small a and small b. Okay, so this is proportional. So this is law of mass action, and so if you multiply a proportionality constant Kf, then basically this is basically called as the rate constant for the forward reaction, and this does not depend on the concentration. Okay, it depends on other aspects but not on the concentration. Alright, so now if you want to write the expression for the change of concentration of A, then basically it is proportional to the rate of change of concentration of A is equal to the change in number of moles in the reaction process minus A times the rate constant in the forward direction times your concentration of the reactant participating reactant species raised to the power of the stoichiometric coefficients, right? So this is your expression for dA by dt. Similarly, for species B, you have the expression as minus B times Kf times A to the power A, B to the power B. And similarly, you can write the species consumption production rates for C and D. Okay. All right. So in this case, we have assumed that this process is happening in one direction. All right. But in practical scenarios, you typically have dynamic processes in which the the forward and backward reactions can happen simultaneously. Alright, so because like all your reactions are happening because of some kind of a molecular collision happening or radical collision happening between these species that are present. So once you start producing C and D, the radicals C and D, radicals C and D can also interact with each other and lead to back production of A and B, right? So the reactions can happen either in the forward direction or in the backward direction, correct? So the reaction rate of AB is expressed as Kf times the participating species, and reaction rate of CD, so that means the reverse reaction is happening, that will be another constant, rate constant, that is corresponds to the reverse process, that times your C and D. Okay, so now if you have this happening, so what will be the expression for dA by dt? So in this case, if you have a reaction that can happen in the forward as well as the reverse direction, so what is going to be the expression for dA by dt? Yeah.
minus A into KF.
Minus A, Kf,
A to the power
and B to the power B. That's it. You can have your concentration of A can increase if the reverse reaction is happening.
we can
So you have an additional term AB times
C of
you have the, so for the reverse reaction your participating reactants are C and D. So you will have this, right? Okay. So the overall, the net reaction rate or the net rate of production of A or consumption of A is given by the summation of the consuming part that is coming from the forward direction and the producing part that is coming from the reverse direction. Okay. Similarly, you can write expressions for B, C and D. So typically when you look at elementary reactions into combustion kinetic models, they are expressed in this form, and your simulation software basically takes into the overall effect of both the forward and the backward directions. So if you write a generalized in the generalized form of a reaction, so mu I is the coefficient for each of the species mi, and mu j, mj are basically the coefficients on the product side. So the reaction rate in the forward direction is nothing but the rate constant for the forward direction times the product of all the participating species on the reactant side. Similarly, you can have the expression for the reverse direction as well. Okay. So now that we know what is the expression for this reaction rates, we want to understand how we can get the values of the rate constants. Okay. So the concentrations are something that you can get by measuring the species. But in order to estimate what is the, determine what is the reaction rate, you need to calculate also what is the value of Kb. Okay, what is the Kb or Kf, which is called as the rate constant. So typically the rate constant is expressed in terms of this Arrhenius exponential form. So you have A, which is called as the pre-exponential factor, T to the power B, you have a temperature dependency with a temperature coefficient B, and then you have something called as your activation energy that is required for a particular reaction. Alright, so what we see here is, so the rate constant is dependent on some temperature, right? And then it is also dependent on the activation energy divided by RT. So what is the activation energy for a reaction?
Minimum energy plus start.
Yeah, so minimum energy that you have to, it's like an energy barrier. So when your molecules or radicals are interacting with each other at a molecular scale, right? So you have, let's say, two molecules that want to interact with each other. So all the interactions are happening via, so the assumption is through elastic collisions, right? So the energy of these molecules have to be sufficient enough so that they collide with each other, break or form the bonds, right? So there is an what do you say, minimum energy that is required to have these molecules moving at a certain speed. Okay, so the activation energy is basically representing that that component of a reaction rate. Okay, so if you look at the exponential factor E minus exponential of minus E by RT versus temperature, you see that with high activation energy processes, the rate constants are going to be very, very small. This exponential component is very small. So even if you go from 300 Kelvin to very high temperatures, 2000, 3000 Kelvin, you see that this component is very, very small. So for processes that has a very low activation energy, like for this, you see that even at small temperatures, the exponential factor is very, very high. So that means that these reactions that have a low activation energy can get triggered very, very fast. Okay. So that will determine, so when you have a detailed chemical kinetic process, okay, when you have this kind of processes, so depending on the activation energy of these reactions along with the concentration of the species, that is going to determine which reactions are going to dominate for a given condition. Okay, so there are several research groups that basically work on determining these rate constants, okay, because they are critical to estimate the reaction rates, which again feeds into the CFD simulations. Okay, so if you look at a typical detailed kinetic mechanism file, so you can see this, these are the elementary reactions. So there is an oxygen atom reacting with hydrogen molecule, giving H plus OH, and for this particular reaction you have A, B and EA that is given to you. Okay, so a series of reactions are basically listed in a chemical kinetics mechanism file with the corresponding values. Okay, and some of the leading groups who develop this kind of detailed kinetic mechanisms are in Argonne, MIT, Lawrence Livermore. Then you have University of Galway, Crack modeling group by Polytechnic, Milano and Kaust. Okay, so these kind of mechanisms. So if you are using a particular kind of fuel, yes.
So I'm assuming that the activation energy is also dependent on the temperature, because the collision as temperature will rise, the collision will be more. So does the temperature affect the activation energy?
No, activation energy is a property that of the reaction process itself. Okay, so the component of E minus EA by RT is temperature dependent. Activation energy itself is not. Activation energy is like the energy barrier that is required to carry out that process. Okay, so that is constant. Now, depending on the temperature that you provide, this component will vary. Alright, so for this reaction, this is the activation energy. Okay, and depending on the temperature feed, it will calculate the rate constant. Okay, so if you want to use a particular fuel, so there are online databases that are available. So if you want to use a certain species, so let's say I'll just show you a few sources which you can use. So this is one of the modeling groups, and these are freely available. So if you want to use a certain type of fuel, you want to study a certain type of combustible matter, you can go to these research groups websites, and there are kinetic mechanisms that are available, right? So if you scroll down, okay, so you see these for different fuels, right? Hydrogen, ammonia, methane, natural gas, methanol. So they have these different detailed kinetic mechanisms that have been developed. Okay, so this is one group. Then further you also have University of Galway mechanisms. Okay, so these are your different mechanism versions that they have developed over the years. Okay, and these are for different fuels. So they have for hydrogen syngas. Okay, the syngas is nothing but hydrogen CO combination. Then they have built for the various types of alcohols, methanol, ethanol. Right. So now if you open one of these mechanisms, okay, so let's download it. Okay, so if you, let's open one of these mechanisms. So these are the different mechanisms that are there, already downloaded. This one. Okay, so this is a chemical kinetic mechanism file. Alright, so what it details is, so if you scroll through, so it first shows what are the different elements that are involved, okay, participating elements, and then what are the species involving these elements, what are they made of. Alright, what are the species that they have, so you can see a huge number of species. Alright, and after you define the species, and it's, yes, it's an extensive mechanism. Then you get into the reaction classes, okay, reaction rates. Okay, so what you can see now here is, now each of these is like a elementary reaction, and with each of these elementary reactions you have these three parameters that are given to you, like we saw, right? The pre-exponential factor A, then the temperature coefficient, then EA, activation energy. So each of these is defined in this detailed chemical kinetic mechanism files. Okay. So along with that, you also have two other complementary files that you need for simulating your combustion processes. One is a therm file, that we using which, like for each species, using these are basically polynomial functions of temperature. So using these coefficients, it basically calculates things like your specific heat, thermal conductivity, diffusivity, using the therm and the transport file. Okay. So along with the mechanism, okay, chemical kinetic mechanism file, you also need to use this therm and thermophile and the transport file. Okay. So, alright. So these are some of the online freely available databases. So for if you want to simulate or study some particular kind of fuel, you can access this kind of databases and get the corresponding kinetic mechanisms. Any questions?
Sir,
Yes.
can you please go to that reaction file?
Reaction file? Sure. This one's?
Yes, sir.
Yeah.
So, if some elementary reaction is present in some mechanism,
Sure.
so the EA and all those properties, and if the same reaction is occurring for some other fuel also, they both will be different definitely, right?
No, the elementary reactions are going to be the same. I'll just come to that. So how we build this mechanism. So this is a, so for example, this is a reaction between HO2 and CH3COO, right? So this reaction will happen when you have sufficient amount of these two species. Alright, and the source of these two species is not, we are not interested in. It could be, so fuel A, fuel B, fuel C, or situation A, situation B, situation C. If you form enough number of concentration of these species, along with if the temperature is sufficient enough so that it can jump the activation energy, then this reaction will happen. So typically when we try to build, previously when they were trying to build these mechanisms, they were looking at very specific fuels. Right, so when they build these mechanisms that are constrained to specific fuels, then the reaction rate parameters that they employ, they used to tune it so that it matches. The model is well tuned so to match the experimental results, and now those models can be used for other simulations. But again, the validity of those models are specific to those particular type of fuels. Okay, so to build a more universal, comprehensive mechanism like one of these ones, you need a lot more number of experimental tests with different types of fuels, different conditions, and different types of experiments as well. Okay, so right, so on that, on that thing. So initially, like what I just mentioned, So previously when the mechanisms were being developed, they were being developed based on just a single fuel, constrained to a single fuel. But recently what has been happening is they have been making attempts to build comprehensive kinetic mechanisms. Right? What do you mean by comprehensive? So it can address these various types of fuels using the same mechanism. So the reaction rate parameters that are there, they are constant. You are not going to change if the fuel is changing. So what we do is we basically start with the simplest species, hydrogen oxygen species, right, reaction system that has 12 species and 33 reactions. And slowly on top of that we build the C1, C2, C3, C4 and so on. Okay, so we gradually build this detailed chemical kinetic mechanisms for all the species that are of interest from a simpler molecular scale. Okay, so in this case what happens is, if you want to simulate a hydrogen fuel system, then you don't have to change the mechanism, you can use this. For example, if you want to use a dual fuel system, hydrogen natural gas or hydrogen heptane, then still you can use this comprehensive mechanism that has your reactions, elemental reactions for N-heptane as well as for your hydrogen. So they are internally consistent with each other.
But the values of EA and all that will vary, no sir?
The activation energy for each of the elemental reactions are going to be the same. Okay, so let's say you are looking at a reaction that is that gives you, okay, so this is one of the elementary reactions. Okay, now this can form in a hydrogen oxygen system, or it can form in some other system. So now this does not react directly, so it has a series of breakdowns. So this fuel will basically break down into a number of simpler species, and that might produce an hydrogen in between. Now when that hydrogen reacts with oxygen atom, it still will follow the same elemental reaction parameters. It is not going to change between the two species.
Okay, EA will be same, all other constants of the Arrhenius equation will also be same, sir?
Or will also be same. What will change is your concentrations. So your H2 and O, they might be changing depending on the situation that you are simulating. But your A t to the power b exponential of minus EA by RT, these are basically coming from the reaction mechanisms. Okay, and the concentrations are being simulated through conservation equations. That will change. Alright, so what has been the recent efforts are building this comprehensive mechanism so that you can employ them to study various multi-component fuels and things like that. So on top of this combustion mechanism, you have additional submodels like alcohols, NOx, aromatics, so that you can study emissions, in fact, emissions predictions as well. Okay, so we can see that. So these simulations were done for ignition delay for different types of fuels, and all these fuels were basically run by a single comprehensive mechanism. And you can see that they are able to predict the ignition delay times for these various kinds of fuels, right? So what happens is, now we have various reaction classes that are taking part in these in this ignition delay simulations, depending on the temperature at which you are subjecting these fuel air mixtures to. Okay, so now these are the different reaction classes. You have a low temperature chain branching reaction, you have an intermediate reaction class, and you have a high temperature reaction class. Alright, so all these reaction classes are involved in, included in your detailed chemical kinetic mechanism file. Okay, so you can see, like, based on the type of reaction, you can basically estimate, like, calculate what are the different, estimate what are the different values for A, the temperature coefficient and the activation energy. So yeah, these are the different reaction classes, and for each fuel you can have these as a submodules. So typically, like, if you run a reaction pathway analysis for a methane combustion system, you see that your methane basically breaks down to produce CH3, right? Then this CH3 basically oxidizes to form CH3O, CH3O2, and then it basically goes to ultimately form CH2O, then HCO plus H2O2, then CO, and then finally to CO2. So in reality, your the process of conversion of a fuel or any combustible material to products of combustion is going through a multiple steps through a complex process. Now the accuracy of this process is basically determined by the accuracy of the elementary reactions that you are putting in this detailed chemical kinetic mechanisms. Okay?
Sir,
Yes.
is there any open software is there so that we can make elementary reactions?
Okay. So you can. So there are some softwares which you can use to generate chemical kinetic mechanisms. Alright. So there is a reaction mechanism generator that was developed by Professor Bill from MIT, and that is freely available. But apart from that, if you want to use a fuel or you have a certain fuel that you want to study, you might do a literature survey. There are groups who have already developed these kind of mechanisms and they are well validated, so you can use them. Alright, so the way these mechanisms are being developed is basically if a reaction rate parameters are not well validated or they are not accurate, then your predictions of flame speed, ignition delay are going to vary compared to your actual experiments. Okay, so in that case you have to study more about the particular elementary reaction rate and update those values in the chemical kinetic mechanism file. Okay, for example, I'll just show I'll just show this last point. So so this is again NIST has a chemical kinetic database. Now, if you want, as you mentioned, if you want to look at a particular elementary reaction, for example, let's say you want to find out what is the reaction rate parameters, rate constant parameters for, let's say, CH4 plus OH giving CH3 plus H2O. Okay, so this is one of the first steps. H2O, and if you submit, then this basically will give you, so it shows that for this particular reaction, elementary reaction CH4 plus OH giving methyl plus H2O, there are already 118 records of past studies by researchers that they have done. Okay. So if you now scroll through this, you can see that what is the reference who has done those studies for that reaction, and the corresponding reaction rate constant parameters are also given to you. So depending on, like you can look at the more recent studies, like you have results from 2020, 2012, so you can look at the recent ones and you can adopt them into your mechanism so that you build it more accurate. Okay, so these kind of data are openly available. So you can, if you want to have if you have a combustion kinetic model that is not working well for your situation, then you can explore if there are any updates to these kind of reaction rate parameters, and you can adopt it and test it. So this is one, and the other one is reaction mechanism generator. So again, this is also available. So here also, right? So here also you can do a kinetic search, and you can basically give what kind of reaction you want to look at. So C basically comes. So you have identified. So C basically represents methane. OH is the OH radical. All right. That gives, so we are looking at a particular reaction, and these are the various, so this also gives you a kinetic search, so which you can use to basically update your reaction. So now these are the reactions studied by various groups and published in recent literature, and based on that you can basically get what are the values of A, temperature coefficient, and X, activation energy values. Okay, so if you are having a chemical kinetic mechanism and it's not working, then you can, and if you are unsure about any particular elementary reaction, then you can use these databases to update your models and then test and validate. Okay. So again, mechanism validation also needs to be done very extensively so that you know that you are not over tuning your model to a particular condition. So for example, if you look at this validation process. So for example, let's say we are developing a comprehensive mechanism that you want to handle hydrogen CO mixtures and methane mixtures. So once you develop the mechanism, it has to be validated for all of these fuels, right? And there are different parameters that you can validate: ignition delay, speciations, speciations and flame speed. Okay, so these are the different validations that you have to do extensively so that the mechanism that you are developing is very, very accurate. Okay, and many of the groups are already working, so as engineers, you can basically take these mechanisms and use it in your simulations. Alright, so with that, we'll stop this session. And any questions?
So you mentioned about H2O2, C1 to C7 species and reaction, what about alcohol and oxygenated and NO2 and aromatic?
Yes, so when you develop these mechanisms, so you are developing a hydrogen model. On top of that you have a CO model, on top of that you have methane and so on. So for, let's say you want to also include methanol or ethanol. So you develop the reaction module for methanol, ethanol, specific to those fuels, and then you add it on top of this H2, H2CO and H2C1 models. Right, when you integrate that, so you can form an extensive mechanism that can simulate alcohol fuels as well. Okay.
But they won't have any species.
They will have species. So for that you will have specific species to that. So it is like a plug and play system. So in the base you have your hydrogen oxygen reaction system. Okay. So on top of that, let's say you have the H2CO system, that is the next complex thing. On top, so on this now you are building, let's say, methane. Right, this is where we have got. So now this methane will be having reaction specific to methane, like CH4 plus OH, right, CH3 plus O and stuff like that. Okay, which reactions you will not see in hydrogen oxygen or hydrogen CO systems. Correct. So once these reactions are taking place, it will produce some intermediate species that has H, OH, and those elemental reactions are already there in this. Correct. Now if you want to add a let's say methanol model, right? So now you have reactions that are like specific to methanol molecule. So like methanol plus OH gives you CH2OH plus H2O. Right, so this will have some kind of a reaction rate constants, reaction rate parameters, and then similarly this CH2OH will further reduce to HCHO aldehydes and other species, right? So those specific reactions will be there in the methanol reaction submodule. Okay, but what needs to be done is you don't have to redevelop these reactions. You can build this and include into your kinetic mechanism file. Okay, for example, if you do not have methanol in your system, if you don't want to simulate, then you can basically take this reaction class out so that you don't have to solve for the species conservation equations for these systems. Alright, so
it will be like just unburnt fuel or like that.
Sorry?
It will be like an unburnt fuel or like
they are not, so they are not in the fuel system means when you are defining the fuel composition, methanol's mole fraction is going to be 0, right? So they are not there in your fuel system, so it will not even consider calculating the reaction rates for them. Okay.